Slide 1, Inorganic Basis of Life. Hello everyone, and welcome to our first lecture on the inorganic basis of life. I'm Muhammad Shahid Nadeem, and I'll be guiding you through this fascinating topic. We'll be exploring the fundamental inorganic compounds that are essential for all living organisms. Let's start with the basics. An atom is the smallest unit of an element, and molecules are formed when two or more atoms combine. When these atoms are from different elements bonded together, we call it a compound. A substance is a pure form of matter consisting of only one type of atom. The periodic table organizes all known elements, currently totaling 118. Each element is represented by a unique chemical symbol, a notation of one or two letters. For example, Cl is the symbol for chlorine. Atoms are the fundamental building blocks of the universe. They consist of negatively charged electrons, positively charged protons, and neutral neutrons. The number of protons defines an element, while electrons orbit the nucleus in specific regions called orbitals. Electrons are arranged around the nucleus in specific shells or orbitals, a concept known as electronic configuration. The 28818 rule describes the maximum number of electrons that can occupy the first 4 energy levels. This rule is particularly important for understanding the behavior of elements beyond the first 20 in the periodic table. Valency refers to the combining capacity of an element. It's determined by the number of electrons an atom needs to gain or lose to achieve a stable electron configuration. Understanding valency is crucial for predicting how elements will interact and form chemical bonds. A chemical bond is the attractive force that holds atoms or ions together to form molecules. There are several types of chemical bonds, including ionic, covalent, and hydrogen bonds. Ionic bonds arise from the electrostatic attraction between oppositely charged ions. Covalent bonds are formed when atoms share electron pairs. This sharing allows atoms to achieve a stable electron configuration. Hydrogen bonds, on the other hand, are weak attractions between a hydrogen atom in one molecule and a strongly electronegative atom in another. Water, a neutral and highly stable molecule, has a very low tendency to ionize. However, it does undergo slight ionization, forming hydrogen ions, H+, and hydroxide ions, OH. In reality, free protons don't exist in solution. They associate with water molecules to form hydronium ions, H3O+. The ionization constant, denoted as Keck, describes the equilibrium between reactants and products in a reversible reaction. For water, it represents the ratio of hydronium and hydroxide ion concentrations to the concentration of water. At room temperature, only a tiny fraction of water molecules are ionized. By substituting the concentration of intact water into the equilibrium constant equation and rearranging, we can derive the ionic product of water. Kw is a constant value at a given temperature and represents the product of hydrogen and hydroxide ion concentrations. This is a crucial concept for understanding acidity and alkalinity. In pure water, the concentration of hydrogen ions is equal to the concentration of hydroxide ions. This leads to the concept of pH, introduced by Sorensen in 1909, which expresses hydrogen ion concentration on a logarithmic scale. pH is defined as the negative logarithm of the hydrogen ion concentration. For pure water, the pH is 7, indicating neutrality. Similarly, the pOH, which represents the negative logarithm of the hydroxide ion concentration, is also 7. The sum of pH and pOH is always 14, reflecting the inverse relationship between hydrogen and hydroxide ion concentrations. Substances can be categorized into 3 groups based on their effect on hydrogen ion concentration. Acids increase hydrogen ion concentration, lowering the pH. Bases decrease hydrogen ion concentration, raising the pH. Salts formed from the neutralization of acids and bases generally do not alter the hydrogen ion concentration. Different scientists have proposed various definitions of acids and bases. Arrhenius defined acids as substances that donate H+ ions and bases as substances that donate OH ions. Bronsted and Lowry defined acids as proton donors and bases as proton acceptors. Lewis defined acids as electron pair acceptors and bases as electron pair donors. When an acid donates a hydrogen ion, the remaining species is called its conjugate base. For example, when hydrochloric acid, HCl, donates a proton, it forms chloride ion, Cl, which is its conjugate base. Understanding conjugate acid-base pairs is essential for understanding acid-base reactions. Conversely, when a base accepts a hydrogen ion, the resulting species is called its conjugate acid. For example, when ammonia, NH3, accepts a proton, it forms ammonium ion, NH4+, which is its conjugate acid. These concepts help us predict the direction and extent of acid-base reactions. Bioinorganic chemistry explores the roles of inorganic compounds in biological systems. It focuses on essential inorganic compounds like water, salts, acids, and bases. It also investigates the structure and function of biologically active metal complexes. Elements can be classified based on their abundance in living organisms. Bulk elements like hydrogen, oxygen, carbon, and nitrogen are required in large amounts. Essential elements are those with specific roles in sustaining life. Essential elements include sodium, potassium, magnesium, calcium, and several trace metals. These elements play crucial roles in various biological processes, such as enzyme function, nerve transmission, and oxygen transport. Their presence, even in small amounts, is vital for maintaining health. This table shows the recommended daily doses for some essential elements in a 70 kilograms human body. Deficiencies or excesses of these elements can lead to metabolic disorders and diseases. Maintaining a balanced intake is crucial for optimal health.